Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.8 on discrete curves. Okay, so we've talked about elliptic curves um, in a continuous sense with x and y, but what if we were to think of this with modular arithmetic? All right, so looking for like pairs of x and y, mod 7, that satisfy this equation. Well, then we'd get some points like this. So this axis is like 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, and similarly going up that way for y and for x. And really, we're just going to be plotting points. And we'll call this a discrete elliptic curve. Okay, now how do we get these points? We find xy pairs that satisfy this equation in the mod. Let's see, and in particular, we can, like if we plug a value of x in, we could take a square root of that to find y. You think about taking square roots in the following way. All the by looking at like 3 bars, the first, second, third, fourth, fifth, sixth, we actually get the non-zero elements of mod 7 all as powers of 3. So thinking of powers of 3, then if we rewrite 4 bars of power as like 3 to the 4th, then we know what the square root is, plus or minus. So that allows us to be able to go in and plug values of x in, find what values of y work, and be able to get a curve. It also, you'll notice that this is, you'll notice some symmetry in this picture right here. For a particular x value, there are two different, if you plug that x value in to the equation, you'd get, so into this equation, you get 2 square roots plus or minus, plus or minus, plus or minus, plus or minus. So we can get our different points in that way if we wanted to map that up given an equation. Now, is an elliptic curve, can really elliptic curve addition still work? Remember that one thing that we needed for our curves before was we didn't have a 0 over 0 situation when we were finding slope. Here, we don't want a 0 bar over 0 bar situation. Can we really visualize what slope is and so forth? Well, we can with a little bit of effort, but at least computationally, algebraically, we can take derivatives here, and then in mod 7 arithmetic, where we're just kind of using the basic definition of derivative rules, with polynomials and powers and stuff. Here, this is implicit differentiation, and okay, and then we think, okay, well, what happens when this part is 0 bar? Well, then the equation, okay, if this part is 0 bar, then we would end up getting 3x squared plus 3, which would mean x squared is equal to -1 bar, which okay, which and -1 is 3 to the 3rd, which has no square root, so that can't even happen. You can't even have a 0 over here in this particular setup for this particular elliptic curve. So we can't even get a 0 over 0. So this really is a nice elliptic curve that we really can use if we're thinking about slopes, at least. Does that really work, though? Let's take a look at the next little subsection. Adding 2 points on a discrete curve. All right. So, all right, let's suppose that we have 2 points on a discrete curve. Okay, so we have an equation of a line, and this line mod 7, and this line also 2 points on the discrete curve also satisfy this. The question is there a third intersection point on the discrete curve that also satisfies this? Let's see. Well, if x1 and x2 both satisfy the equation, all right, so let's see this equation, we're at the intersection, right? The intersection. You take this, replace it for y, put it in here. So this is the equation of the intersection. And let's suppose x1 and x2 both satisfy this. Let's rearrange this. So we get this. This is a cubic in x. This is a factor. Okay. This is a factor. X minus x1 and x minus x2 is a factor of this particular polynomial. Mod 7. Now, if we're working mod 7, actually, we'll take it for granted right now, but this is not something you can assume normally. However, we're arithmetic over mod 7 is actually arithmetic in a field, and we have unique factorization actually of polynomials if we take coefficients in that field. So a field is just something where you have this nice structure of addition and multiplication working together nicely, where there's only one, where every element that's not zero actually has an inverse, and that works, especially when you're modding out by a prime. And so when you're modding out by a prime, this does work. Okay, so let's suppose that this is a factor. All right, and all right. Okay, then notice you can do polynomial division, and in that polynomial division, you get you get a remainder of 0, and your quotient is going to be a first degree, and that first degree will actually give you a third x value, which is on, and if x value, that will describe a point of intersection. A section between the two equations. All right, so we end up getting now. So we end up getting a third point. So this x3 will be an x value, which will make the y values the same again for those. So we get so that's great. So we have 3 intersection points. Then we can just use kind of a vertical partner type deal with just making negatives, making the y value negative that we got here to get the sum. So it really works the same way. So we can come along and look at this example here. Suppose you have a point here and a point here, and you want to add them together. Suppose you know that those are on the line. So, well, first of all, let's find the equation of the line that actually passes through these points. You need to find the slope between these. Slope, done the same way like rise over run. Go 1 minus 3 over 4 minus 0. But when you divide, it's like multiplying by the multiplicative inverse. So the multiplicative inverse of 4 is 2, because 4 times 2 is 8, which is 1 mod 7. Okay, so it's like multiplying, and 1 minus 3 is like negative 2, which is 5 mod 7. So we have 5 times 2, which is 10, which is 3 mod 7. So we end up getting 3 bar as our slope. So we're kind of looking at 3x. And then actually, because we actually have the y-intercept here, because when this is like our x is 0, so y is 3. So we end up getting this equation right here. Y is equivalent to 3x plus 3 mod 7. So we can plug that in here in for y, replace it, and multiply it out, rearrange it, and that's our this, and we solve for x to find our third intersection point. We need to divide by this, because this is like x minus 0, x minus 4, because we have an x value of 0 and x value of 4. So we say x minus 0 times x minus 4, and if we divide that into here, look at the quotient. Notice 7 is 0 mod 7. That's like kind of what we wanted, because working mod 7, that's important to remember. So we get x plus 2, which means that the third intersection point happens at x equals negative 2, or congruent to negative 2, which is the same as x is congruent to 5, or x is equal to 5 bar. So, okay, so then we can plug in 5 bar either to solve for y. Actually, it's just because it's going to both be on this line and on that curve. So we may as well just plug it in here to find out what y is. So you plug in that, which is 5 bar, into that equation, and you okay, into that equation. Um, or you could do that, or I guess here we took a square root. We plugged 5 into the equation. We got 2 square roots, and we saw which one was actually on the curve. And okay, all right. Well, we just plugged it into the line here, but nonetheless, it's 4 bar. Okay, so we get 4 bar. So 4, so 5, so 5, 4 is the is that right? Yes, so 5, 4. That's the third intersection point on the line. So that's on the line. That's the third intersection point. But the negative 4 is actually 3. So that's the vertical partner. So 5, 3 is on the line now. Now with symbols, remember where 5, 3 was in this little graph here. 5, 3 was we labeled it as a point 2. Hence, we just computationally showed that that these 2 points added together, labeled as G and C. If we look at so we had G, which is 0, 3, and C, which was 4, 1. We add those together, we got 2. Okay, so we actually have a nice addition process, well defined, even in the modular arithmetic case. All right, but do we always want to do that? So there's a visual way of doing that. So we showed you that way before. We see how to do it visually, and that'll be in the next little video. Thanks for watching.